Hey, how's it going? Mr. Farah here with another physics video, and today we are talking about the transfer of heat and the change of temperature. Now, we've been using the specific heat capacity equation a bit recently, and now we are going to focus on using it in a particular way or a new way. So the way we're going to focus on today is when you have or are given the amount of energy added to a system or the amount of energy taken away from the system, you're now going to be able to calculate how much the temperature of that system will change, okay? So in this problem that we see on the board, it reads 3,278 joules of thermal energy or heat are added to 12 kilograms of aluminum. How much will the temperature of the aluminum change? Now, as we can see in this problem, we have the amount of energy. We know the heat that is being added to the system, but we don't know how much that system will change its temperature or what will be the temperature change of that system. So that's what we're going to calculate. So as with any problem, we're going to first write out our ICE method. I-C-E-E. Okay, ICE again stands for identify, categorize, equate, and evaluate. So my first step here is to identify all of the measurements that I see in the problem and to just acknowledge that there is a question being asked. Okay, so let's go ahead and go through this problem and try to identify those measurements. So remember, a measurement is any number and its units. So here I see 3,278 joules, that's one measurement. 12 kilograms is another measurement. And that looks like all of our measurements, okay? Now, I know that a question is being asked of me as well, okay, which I could underline, if you want, but it's gonna be this last sentence right here. That seems to be the question that's being asked of me. And so again, we're going to come back to that and really try to identify or figure out what that question is a bit later, okay? But right now, we just need to know that the question is there. All right, so we're going to go ahead and write our measurements. So 3,278 joules, okay? And then 12 kilograms, you see that, all right? And again, I don't need to know what that question is. I just needed to identify that there is a question being asked. Okay, so I wrote my question mark there. All right, now we've identified all of our measurements. We've identified that a question is being asked. So it is now time to categorize these measurements. So we need to figure out what variable represents each of these measurements. What variable even represents my question? So we're going to start with 3,278 joules. Now, this is a tough one to start with off the bat because joule is a unit of energy. So there are many different variables that describe energy. Kinetic energy describes energy of motion. Work describes energy that is used to do something, do some task. Or we could be talking about thermal energy, right? Or heat, that is energy of temperature changes and fluctuations, right? So we see joules, but we need to go back to our problem to figure out what type of energy this is. Now, we find it out rather quickly. It says 3,278 joules of thermal energy or heat, okay? Now, because we know it's thermal energy or heat, we know that we can represent this with the letter Q or the variable Q, okay? Now, let's look at kilograms. So 12 kilograms. We see kilograms, we know that is a unit of mass, so we'll go ahead and write that there. And now we need to figure out what is our question, okay? Now the question that we've underlined says, how much will the temperature of the aluminum change, okay? Now, there are a lot of words here, but what you really want to pay attention to is what variable are they telling you to focus on? And here it says, how much will the temperature? So temperature is the variable that is changing here. And it's asking us how much will the temperature change. So how would we represent the change in temperature? Okay, we do T for temperature, so capital T for temperature, and then a change in temperature is just represented by the Greek letter delta. Okay, so let me rewrite this actually underneath an arrow. So delta T is going to be our change in temperature. All right, so how much is the temperature change? We're looking for delta T. Now that we have these measurements here, we can go ahead and plug them into an equation. Okay, now the specific heat equation can be written in a number of different ways. I'm going to write it the way that I've actually been using recently with my students. All right, so that is in the form mass times delta T, change in temperature, times the specific heat capacity of the material is equal to the heat energy transferred. Okay, now again, if you wanted to write this in a different way, you could go ahead, divide by your mass, divide by your specific heat capacity on both sides, and that would allow delta T to be by itself, and you have Q divided by M times Cp, okay? Heat divided by mass times specific heat capacity on this side, and you just have delta T on this side. So if you want, and you're strong in your algebra work, go ahead and do that. I actually prefer doing it that way. But we're going to go ahead and use this equation, and we're going to plug in our measurements as this, just in the equation as it is. So let's go ahead and do that. Again, before we do that, acknowledging what these variables are. M is the mass of our material. Delta T is how much that material is going to change its temperature, which is what we don't know. Cp is the specific heat capacity of our material, okay? And Q is the thermal energy or the heat energy that is transferred, either being added to our material or leaving our material, okay? So we're gonna go ahead and write our mass as 12 kilograms, okay? Our change in temperature, we actually don't know, so we're gonna leave that as delta T. And then our specific heat capacity. First, in order to figure this out, we need to identify what material we're talking about. And the material we're using in this problem is aluminum. Okay, so the specific heat capacity of aluminum that I have, just having looked it up, is 899 joules per kilogram times degrees Celsius. Okay, now again, sometimes you'll see this written as joules per kilogram Kelvin. That is also true. The reason we're using degrees Celsius here is because we're going to measure our temperature change in degrees Celsius. If you wanted to use Kelvin here, you just measure your temperature change in Kelvin, which is totally fine, okay? And now on the other side of this, and one more time just explaining, this is saying it takes 899 joules of energy to change the temperature of 1 kilogram of aluminum by 1 degree Celsius, or 1 Kelvin, okay? So let's go ahead and write our heat energy on the other side of this equation. So that was 3,278 joules, okay? So I like putting everything in parentheses. It just helps me see it all better. Now here, we can go ahead and begin solving this problem, okay? So for starters, let's go ahead and multiply our 12 kilograms by 899 joules per kilogram times degrees Celsius and see what we get. All right, so we went ahead and multiplied these together. Now again, the reason we can do that is because this is multiplication. So it doesn't matter which order we multiply these numbers in, because all of this is just multiplication. So when we multiply 12 times 899, we get 10,788. So I'm going to write that here, 10,788. Okay, and now my units. So here, my kilograms, I have this kilogram in the numerator and this kilogram in the denominator, so I can cancel those out. All right, and I'm going to be left with units joules over degrees Celsius. So I'll put that here, joules over degrees Celsius. All right, and this is still being multiplied by delta T, okay? And then that's going to equal 3,278 joules. All right, so now I've got one number on this side, one number on this side. in order to solve for delta T, I have to divide by this number. Now that is because this number is being multiplied by delta T. That's what's holding them together. So in order to separate them, I need to break them apart by doing the opposite of what's holding them together. So multiplication is holding them together, so I'm going to divide in order to separate them. I'm going to divide by 10,788 joules over degrees Celsius on both sides. All right, 10,788 joules over degrees Celsius. Okay, cool. So when I go ahead and divide these, they cancel out, all right, because I have the same thing in the numerator as the denominator. So I am left with delta T by itself on this side. Over here, I'm gonna have to multiply these two to get a number, and I'm running out of some board space up here, so I'm gonna go ahead and erase some of this. Okay. Right, so on the left side of the equation, we still had our delta T, and that was equal to 3,278 joules divided by 10,788 joules over degrees Celsius. Okay, cool. So let's go ahead and divide through our numbers, okay? So 3,278 divided by 10,788 is going to give us 0.30, let's see, 0.30. And instead of putting 3, because there's an 8 following it, we're going to round this 3 up to 4, okay? Now we need, and we know that's going to be delta T, okay? But now we need to figure out what our units are. So we divided 3,000 by the 10,000 to get our number. All right, now let's go ahead and figure out our units. So this J, this joule, is up top in this fraction. This joule is below this fraction line, and so we can cancel those out. Now, this is where it gets a little tricky. This degrees Celsius is in the denominator of this denominator, which means we flip it all the way to the numerator. Now, to show you briefly why that is, if you have, it's because of the keep change flip rule, okay? So if you have 1 divided by, right, because we can write this fraction as 1 divided by 1 over degrees Celsius, right? We could write it that way. So let's write this division sign. Instead of making it a fraction sign, we're going to make it a division sign like this. 1 divided by 1 over degrees Celsius, okay? Because our J's are canceled out already. Now we're going to keep the 1, change our sign from division to multiplication, and we're going to flip the fraction. So now instead of 1 over degrees Celsius, it's degrees Celsius over 1. Now when we multiply these all straight across, we're going to get 1 times degrees Celsius divided by 1, which is going to be degrees Celsius over 1. Okay? And now anything divided by 1 is just going to be itself. So we are left with degrees Celsius in our numerator. Now, if you didn't follow the keep change flip rule of that, I would encourage you to continue to practice that algebra skill, because you're going to use it a lot in physics. But in short, if you see a fraction in the denominator of the denominator, then you flip it all the way to the numerator. So that's a quick way to remember that rule. Okay? So we're going to go ahead and write degrees Celsius down here. All right, because that's what our final answer is. Another way we know that is because we're looking for the change in temperature, and we measure temperature change in degrees Celsius or Kelvin, and so we know that we need to have degrees Celsius in our numerator. So after doing all that math, we see that our temperature change is going to be very small. It's going to be a 0.304 degrees Celsius, okay? Now, let's take a minute to think about what that means. So, we added a lot of energy to this aluminum, but notice there was a lot of aluminum. There are 12 kilograms of aluminum. So to heat up all of that aluminum the same amount, we've got a lot of energy dispersed among that aluminum, and so it's not going to heat up a lot, okay, on the whole. Another thing that we notice is our temperature change here is positive, right? So that means the temperature of this aluminum went up, it increased. So maybe it was at 0 degrees Celsius and increased to 0.304. Maybe it was at 80 degrees Celsius and increased to 80.304. We don't know. But we do know that the temperature rose because we added energy. Now, if this was a negative sign, if negative 3,278 joules of thermal energy, right? If this amount of thermal energy was taken away from the aluminum, then we would expect our temperature change to be negative, right? So if energy is being removed from the aluminum, then our temperature change is going to be negative. If energy is being added to the aluminum, then our temperature change is going to be positive, okay? Awesome. So thank you all again for joining and working through this problem. This is going to be super important in some of the work we have coming up. All right, have a great one.